Hello, my name is Hukkanen, and I'm mostly happy to announce that I have invented/discovered the way to achieve an affordable green transition. I have already obtained one patent, and I will be granted another quite soon. This solution has been reviewed by three professors and a couple of expert PhDs. Kind of briefly previewed it and were not unable to make it not work. And they were that because no one can make it not work. And I will show you in this video why it works. I know everything about this system that's worth knowing, and the numbers are very clear. And the reason to this thing working is that the current understanding, the current paradigm of heat engines efficiency is built on a false idea that it is only the temperatures at the heat engine's entry and exit side that determine its maximum efficiency. That's kind of a weird, because everybody always knew that the pressure, temperature, and the volume were all connected. So why would it only be the temperature? And it is not. I will be showing that with absolute certainty in this video. So, for example, your automobile, it works with only like 25 to 30% efficiency. Most of the energy it consumes goes not into useful work, to multi-power or electricity that powers them a bit later. So it's I was wondering that why is this energy not used, and the solution was quite simple. It is the pressures at the heat engine's entry and exit side that really determines efficiency, and the way to circumvent this current Carnot's theorem as a limit is to condense the vapor at the heat engine's exit side. It will create that pressure difference, and it will be powering the heat engines with over 90% efficiency quite nicely. But let's see first how it is very, very different behavior in systems that you have uh, condensing vapor, or if you have ideal gas or other non-condensing gas inside of a closed container. So the pressure drop, if you have uh, ideal gas in this kind of a closed container system, initially was open, it was heated, the temperature was heated to 100 degrees Celsius, that's 373 degrees Kelvin. The pressure would be 101 kilopascals, and it's the same pressure, same temperature in all of the system. Then, when you close this uh, valve plate here, and you will have still this pressure and temperature on this side, and you will have lower pressure when you cool this side. So let's assume that you cool this side to 0 degrees Celsius, that's 273 degrees Kelvin. The pressure at this side will go down to 74 kilopascals. So there will be 74 kilopascals pressure pressing this plate from this side, and there will be 101 kilopascals pressure pressing from this side. Now that we know that we have a certain cross-sectional area in this plate, both sides. And we can calculate the force. That would be pressure times area. And so it becomes newtons. So we have 100, if we have 1 square meters cross-sectional area on this plate, so we have 101 kilonewtons force coming from this side and 74 kilonewtons force coming from this side. And the calculations are here. So, and what is the most striking observation here is that if you calculate the Carnot efficiency value to a system that has this temperature combination, so you had initially 100 degrees, that is 373 degrees Kelvin, and you then cool at this cold side to 273 degrees, 0 degrees Celsius, you will have a theoretical maximum efficiency for a heat engine system with these temperatures. That would be 26.8%, and it can be calculated using this Carnot's equation. And when we know that we have all the necessary parameters of this system, so we can, if we know that we had 101 kilopascals pressure on this side, we assume that we had 5 cubic meters volume. We know the temperature, it was 373 degrees Kelvin. So we can calculate the amount of substance inside of this half. And we can calculate that using ideal gas law calculator. And PV equals nRT, and we wrote that equation. I can show you that. You can play with that yourself then. Okay, so let's see here. Here, ideal gas law calculator. So if we have here this, we calculate the amount of substance, and we get this from the pressure 101, volume 5 cubic meters, temperature 373. We can get this 163 moles of ideal gas. So, and that is kind of a important value here, because when we know the amount of substance, we can then we have the similar half here. We know that we had initially 163 moles ideal gas on this side also. But after we cool it, we still have that 163 moles of amounts of substance here. Volume will be still 5 cubic meters. Temperature will be cooled to 273 degrees Kelvin, 0 degrees Celsius, and the pressure we can get to be 74 point something kilopascals. So we can check that out here, and so we had this. Let's calculate the pressure. As we know the volume, we know the amount of substance, we know the new temperature. It was 273.50, and calculated, and we got that 74 kilopascals pressure on this side. So we go back. Yeah. So this is the pressure at the exit side if we have ideal gas. We also calculate here so we calculate the forces also. So the plate will be pressed with the 74 kilonewtons force from this side and 101 kilonewtons. And what's interesting is that if we calculate this from these forces, we can put those, this is kind of a new equation. The force coming from this cold side and 1 minus force from the cold side, this right side, and force coming from the hot side, and we get also the same 26.8%. That's the same Carnot's efficiency value, and if we calculate from the pressures, we get the same. So if we put this is the correct way to calculate the maximum efficiency that I say I have discovered and can prove. So this Carnot's equation is bullshit, and this my equation is correct. It gives here the same maximum efficiency value if we calculate from exit side pressure divided by entry side pressure and 1 minus that, and we get that. So we can get the same Carnot efficiency value from many different ways, but which one is correct? Is it from the pressures, or is it from the temperatures, or is it from the forces? Well, we will figure that out now as we have a new system that I mentioned earlier. So if we had that water, we initially would have a similar kind of system. We would boil water. There would be this whole tube would be filled with steam, and then when we close this lid like this, when we had that steam, we had that 101 kilopascals, and at the temperature of 373 degrees Kelvin, that's 100 degrees Celsius. And then we cool, similarly as we did with the ideal gas, we cool this half to 0 degrees Celsius, that's 273 degrees Kelvin. And the pressure drop on this side is very, very different than what it was when we had ideal gas. When we had ideal gas, the pressure on this side was 74 kilopascals after the cooling. But when we have condensing vapor and we cool it to 0 degrees Celsius, we only have, should be pointed, 1.6 kilopascals. So there's half a percentage of pressure, vapor partial pressure left on this side. So this enormous pressure difference will be causing an enormous difference in forces impacting this plate from these different sides. So from this side, we have this 101 kilopascals pressure, and towards 1 square meters cross-sectional area, it will be pressing this plate with the 101 kilonewtons force. But when we have only 0.6 kilopascals pressure on this side, then from this equation we only get the force of 0.6 kilonewtons pressing the plate from this side. So there's an enormous difference. Here we had 74. There's 0.6 when we have condensing vapor. It means that when we cool condensing vapor on this half, the vapor pressure will not be pushing the plate almost at all towards this direction. And this force will totally dominate this force that exists at the this cooled side. So if this force means that is equals kind of for 1 square meter, if you would place that plate 1 square meter plate horizontally, this means that you would have something like 10,000 kilograms weight placed on that 1 square meter area. While in this kind of system where you had gas, the gas was still pressing from this cooled side with the 74, so you had a net force of only something like 26%, 26 kilonewtons. That equals placing a 2,600 kilograms weight on a surface of 1 square meter. So we have the same temperature, same temperature changes, but this force difference is enormous. And if we calculate this using the same, if we make the same calculations as we did before for this ideal gas-filled system, so we can again, if we calculate the Carnot's efficiency, we have that 26.8% maximum efficiency from these temperatures 100 degrees Celsius and 0 degrees Celsius. That's 273 degrees Kelvin divided by 370 degrees Kelvin, or 1 minus that. So that is the Carnot efficiency. But as I mentioned, so when we had ideal gas, we got the same Carnot efficiency values from the pressures, but now we are not getting the same. We are getting, if we calculate that efficiency from these pressures, we get a 99.4% efficiency. So it means that all of this pressure can influence and cause the irreversible deformation to this metal with 99.4% efficiency, because there is no resisting pressure force coming from this side, almost none. So, and if we calculate this from these forces, because these I have found that the heat engines are powered by Newtonian forces. So these are important, these are unavoidable. If you have pressure impacting a certain surface area, both from the entry and exit side, you will have Newtonian forces. So it's kind of a very, very, and in this kind of a system, you can also see that clearly that it is not the temperatures do not give the correct answer, because if the temperatures would give the correct answer, you would have the same forces, same pressures coming from both sides. And for example, let's see here. Mythbusters, they did kind of an experiment with this kind of a railroad liquid container with half an inch thick steel walls. This very, very strong steel walls in this kind of container. And when they caused the pressure that's kind of was equivalent to pressure reduction with the condensing vapor coolant. So this whole structure kind of imploded, and if they had uh, gas that was not condensing with these temperatures, the pressure inside of this would have been lowered by only like 26%. Now that it was lowered by 99 point something. So if they had only gas or air in this, and they had just done this cooling, so it would not have caused any kind of structural damage. And we can see this kind of effect in many of these videos on YouTube, and for example here Mr. Chetchu's Geography channel shows this quite nicely in this experiment. This is actually a machine that does metal deforming work, and in this system they have a barrel. It's filled with steam. There's a little bit of boiling water in this barrel. They're boiling it with some kind of a gas burners that are placed underneath here, and now that they're causing the barrel to be filled with steam, and they have this system water boiling in that barrel. Now they are closing the lid here, and they are removing these burners, and now they began to cool this thing with cold water. So the pressure inside of this barrel will go down as it cools, and there's an enormous pressure drop even if the temperature doesn't change very much. It only changes like some tenths of degrees, but the pressure drop causes this barrel to implode. The volume of this barrel goes down to maybe 10% of what it was a minute ago, and like this. So if you would then tip this barrel to upright position and would begin to feel that the inside of the barrel, you might be able to put something like 20 liters water inside of this. So you can see that the volume has been reduced by 90%, but if you had non-condensing gas inside of it, ideal gas, you would have had its volume to be reduced by less than 18.8%. Basically, would hardly see any kind of volume reduction in that. So, but as you can see with your own eyes, we have the volume reduced to much greater degree than the 20% that would be possible if it contained gas. So this is kind of a demonstration of a machine that operates actually with over 90% efficiency. It's not kind of a very useful machine, but it's a machine. So let's see here calculations relating to this barrel system, and we have those here. So if we assume that we had that hot hot temperature to 100 degrees Celsius, 373 degrees Kelvin, and we then cool it by 70 degrees to 303 kelvins. So for this kind of a temperature combination, the Carnot's maximum efficiency would be 18.77 percentages. And now that what we saw here was a kind of a much greater volume reduction than would the ideal gas law would suggest. So if we knew that we have the hot side temperature 373 kelvins, cold side 303 kelvins, and we know the initial volume was 0.220 cubic meters of that barrel, we can calculate the amount of substance inside of it. We have the initial pressure before they were closing the lid. So we can calculate the new volume as if we assume that the barrel's walls would not be kind of resisting the pressure would be able to equalize inside and outside of that barrel. So the new volume would be 178 liters, and the change of volume would be 18.77%. It's exactly the same as is the Carnot's efficiency value. So what I'm saying here is that the Carnot's efficiency values are linked to ideal gases behavior. And on the other hand, if we had an isochoric process, as we had in that weird tube that we calculated, so we would have a lower pressure and lowering of the pressure with these temperatures, 100 degrees Celsius and 30 degrees Celsius. And we had that constant volume, 220 liters. We have the amount of substance inside of it, and we have the pressure. Yeah. Now after we had closed the lid and cooled it down to 303 degrees Kelvin, 30 degrees Celsius, we would have a new pressure that would be 82.3 kilopascals. And the change of the pressure would be can be calculated from this equation, and the change percentage would be 18.77%. Again, it's the same as is the Carnot's efficiency value for this. So Carnot's efficiency is linked directly to this ideal gases behavior with temperature, pressure, and volume. And when we go and look, let's see, okay, so we can have that here. No, that one. And here, I prove how my invention can escape the Carnot's efficiency limit by showing that the pressure reduction that occurs inside of a closed container, isochoric process, it is a linear pressure reduction. It goes down towards the absolute zero. And the pressure reduction of a condensed vapor is very much different. It's very, very strong. It only needs to have a very small temperature change, but it will be causing an enormous pressure change. And here I have calculated the values that show that the Carnot efficiency values follow this ideal gases pressure reduction in a closed container like this. So if we assume that we have 1 cubic meters closed container that has a certain amount of ideal gas, let's say 41.4 moles of ideal gas. We have the initial temperature, 1089 kelvins. Initial, well, then we calculate how many percentages does the pressure inside of this barrel, box, container, whatever, will go down as we cool it down. So we began from 1089 kelvins. When we cool it to 900 degrees Kelvin, it will be having still 82.64% left of the pressure. And we can see here, it began from 1089 kelvins here. We go to 900 kelvins, it's here. And we can see that it is the difference here. 82.64. And it's for all these values, you can check it out then. And if we know those temperatures, that we had the initial temperature where we had 100% of the pressure. We have that hot side temperature would be 1089. We have some kind of a lower temperature. We can calculate from these two temperatures the Carnot efficiency value. And for example, we can calculate to that 900 temperature drop to that 900 degrees Kelvin from this equation, and we get the Carnot efficiency like this. And if we calculate 100% minus this Carnot's efficiency value that can be removed from the system in a form of work or something, so we get exactly the same percentages from this. So Carnot's efficiency values are clearly linked to the pressure reduction of ideal gas inside the closed container as a function of temperature reduction. So, and here we have those table values for condensing water vapor, and if we have this initial pressure at 101 kilopascals saturated water vapor pressure at the temperature of 303 degrees Kelvin. And as we go down, so we will see that the pressure of the saturated water vapor will be much lower, and we have here, for example, this 273 degrees temperature, 0 degrees Celsius. That way we already had this pressure that was 0.6 kilopascals remain at that. So the pressure reduction was quite total. So, and it's not just the water vapor's pressure that goes down. It's all of the kind of many different possible fluid substances have the same kind of pressure reduction as a function of temperature reduction. Here's the water's behavior, and there are some other possible fluid substances, and they behave kind of similarly. So what we have here now, we can look more closely at what is it really what's going on with the heat engines. So I did write a quite large article that shows it's really the pressures that are powering the heat engines, but with this system I can show it to you in a quite simple way. So if we assume that we have this kind of a system that is initially at rest, we have outside pressure, 101 kilopascals, usual pressure of air. And we have initial temperature there, 294 kelvins, that's 21 degrees Celsius. And we have that same kind of substance here inside of this cube. We know the volume of this cube is 1 cubic meter. We know the temperature, 294 kelvins. We now have the pressure, 101 kilopascals. And the cube is connected to ambient air with this pipe that has a heat engine. Now, we can calculate the amount of substance in this cube using the ideal gas law calculator. And we get the amount to be 41.3 moles. And well, you can calculate those self. And we know how much substance is it in this, and the system is at rest because the same pressure, same temperatures on both sides of this heat engine. But then we add heat to this system, and we get an increase of the pressure. So when we heat this initially 294 kelvins ideal gas to 1089 kelvins, the pressure will go up to 374 kilopascals. We calculate that pressure again using the amount of substance we knew was in here, and like this. So the volume will be still the same, but the pressure and temperature will have gone up. For this system that has the hot side temperature 1089 kelvins and the cold side temperature 294 kelvins, the Carnot efficiency for this kind of system would be 73.003, maybe, was it? And what is that Carnot's efficiency? What causes it to be? A month ago, I talked with the PhD in physics engineering, who was kind of a very expert in this kind of questions. So I asked that what is that causes what's behind the Carnot efficiency, and he began to mumble something about it can be calculated with Gibbs energy. No, it's Gibbs energy. It's only the Newtonian forces, and it comes from this pressures. When a heat engine is operating with the maximum efficiency, it can lower its entry-sides overpressure to the level of exit sides pressure. And when it does so, it for example, in this kind of a system, it removes exactly 73.003% of this pressure, and then it gets this 101 kilopascals pressure as a result. So this is what causes the Carnot's efficiency. And what's most striking is that when you have pressure coming from this side, if we are coming from the exit side, so you can calculate the force, Newtonian forces, if you know the cross section of this heat engines area, surface area there. So you can calculate the force. It would be in this system 37.4 kilonewtons coming from the entry side, and from the exit side it's 10.1 kilonewtons. And when the heat engine has lowered its entry side's pressure by exactly the amount of Carnot efficiency, like this, then it will have reduced the force pressing to the force of coming from the entry side to the level that exists at the exit side. And when the forces are kind of equalized, then it cannot take more of the system. If the heat engine would be able to take more, if it would be operate, for example, with the 75% efficiency, then it would create under pressure here, lower pressure that exists here at the exit side. And if it would do so, the exit side's pressure would be greater than the pressure inside of the heat engine, and the exit side's pressure would begin to rotate this turbine kind of backwards. So it is the equalization of the entry side's overpressure that's behind the Carnot's efficiency value. And you can see it here also. So do you really need heat for heat engines? No, you need pressure. And it can be shown with this kind of a system where you have cold compressed gas released into the same kind of a cube. So the cold compressed gas will create an overpressure on this side. It will be 373 kilopascals. And it will then have again the Carnot efficiency. If there's no temperature difference, Carnot efficiency would be 0%. No temperature difference, but it will be actually this. It's just a reminder here. So, but if we have that overpressure and the heat engine is able to reduce the entry side's overpressure to the level of the pressure that exists at the exit side, it will need to be removing 73.003% of this entry side's overpressure, and the result will be the exit side's pressure. And again, it is the Newtonian forces that are kind of powering the heat engine. So now we have kind of the two main components of the Hukkanen engine briefly introduced here. So we escape the Carnot's efficiency limit by cooling the condensing vapor or condensed vapor. So when we lower the temperature, the pressure will go down. And this one shows that it is the pressures that dictate the maximum efficiency. Because if you have no pressure or lower pressure, the lower pressure you have on the exit side, the less it is able to resist the pressure that's coming from the entry side. As you remember, so we got this. Okay, so let's see the article. Yeah, yeah, yeah. In 2001, I secretly published an article. Uh, I put it on Wayback archive.org, and it shows that the same Carnot efficiency values can be obtained from this equation. And I prove it many ways, and I prove that this is actually the correct equation because this gives the correct efficiency value uh, even when the Carnot's efficiency fails, and it fails in under certain circumstances. So, but I use, for example, this kind of a system for proving that the same Carnot efficiency values can be obtained from both the pressures and temperatures. So in this kind of a system, we again have a very simple system. We have a tube, and we have a heat engine inside of it. We have a hot entry side. We have a cold exit side. Initially, the system is at rest. We assume that we have the same pressures, temperatures on both sides. Then we suddenly heat this side. And as you know, we have 1 mole of gas, and we have the volume here. We know the temperature to which we elevate this temperature. We know the initial temperature. And for example, here, if we had initial both of those boxes at 294 degrees Kelvin, yeah, and then we heat this side to 1089 kelvins, we get the Carnot's efficiency value like this, but we can also get that using the pressures, which we can calculate using the ideal gas law calculator, and we get exactly the same number. And I show here that this can be obtained, or the same Carnot efficiency values can be obtained with a wide range of temperature combinations. And as this system doesn't have anything else, no kind of hidden factors here, something, it's filled with ideal gas, the volumes are known, everything is kind of clear. So this proves that it is possible to replace the temperatures in this Carnot's equation with the pressures. But the Carnot's efficiency fails in certain systems. For example, if let's see, oh, let's take that one. There we are. So in this kind of a system where we have that 1089 kelvins at the heat engine, and we have exit side coming from the enter side, this temperature there, and the exit side's temperature would be the ambient air's temperature, 294 kelvins. We can calculate the Carnot efficiency to be 73%. That Carnot efficiency would then be able to cause motive power to this wheel, so that this car placed on a floating surface would be able to travel somewhere with that kind of a efficiency, theoretical efficiency. But so if the temperatures were those that were determining the heat engine's efficiency, then it would not make any difference if we were pushing those exhaust gases deep into water, as if the water would be at the same temperature. The same temperature of the water, 294 kelvins, as is in the ambient air. And as it takes energy to overcome the hydrostatic pressure of the water, 10 meters deep water here, so you will need to use force to overcome this hydrostatic pressure, and therefore, if you would still have the same maximum efficiency, then you would need to create new energy to this system from thin air. And that's kind of would violate all kinds of physics rules. So, but if we are using the pressures, we can get we can calculate the maximum efficiency quite nicely. Somewhere it is here. Okay, maybe it's that. No, it's not that one. Yeah, I saw some lots of different proofs, and somewhere it's there. So using this my equation with the pressures replacing the temperatures, we can see that the maximum efficiency would when pushing the exhaust gases 10 meters into water would be 46%, while the Carnot is always promising the 73% maximum efficiency for this carbe that you saw the other side of. So, and when you had pressed this to 27 meters deep, so you would no longer have any kind of motive power left for the floating things movement. So this is kind of also what you would expect from the aeration devices that are kind of pushing air into ponds, lakes, and trying to increase the oxygen content there. So it's kind of those can be kind of, if they operate with like 50% efficiency, you might be able to push that to 15 meters depth there. So it's kind of a success that it is experimentally proven. But the better experimental proof is here. Let's see here. So the critical parts have really been proven experimentally, and it's here. Chinese researchers wrote an article, performance analysis of a four-stroke compressed air engine, Zheng and Zhu. Yeah, and at the Wuhan University of Technology. And they found out that when they were powering a four-stroke engine with compressed air, they tried different air temperatures. They found that the heating of the anthracite gas did nothing to improve its efficiency. In fact, it performed a little bit lower when they had higher temperature there. So it was when it's same pressure, but the higher temperature, it performed more poorly. I believe that's because some of the heated air's heat went into the into heating the four-stroke engine. Maybe that was it. But heating that did not increase the air's ability to do work there. And they concluded that compared with the other parameters, supply pressure has a greater influence on the performance of the compressed air engine, and the increase of supply pressure can effectively improve the indicated work and work efficiency. So it's the pressures they found were important, but the supply temperature has little effect on the performance of the compressed air engine. With the increasing supply temperature, the average torque, effective power, and work efficiency will decrease slightly. This is precisely what I'm kind of saying. It's the pressures that are powering the heat engine. And that was kind of also shown quite nicely with this simple thing. All the heat goes for increasing the pressure in heat engine, but temperature is not kind of necessary. If you have that pressure, you will have the system performing the same. So this does not look like your car's engine, but kind of it is the same kind of a system. Your car's engine will take air, and it will have some gasoline there, and will have a spark, and the temperature will go up, and the pressure inside will go up, and then it will cause the motive powers that the engine will obtain from this pressure difference between the combustion chamber and the ambient air. So it doesn't look like the same, but it is. And what is my Hukkanen engine kind of structure? So I have here a very, very simple proof of concept device. And this is kind of a demonstrates a cyclical process, and that obtains with very high efficiency energy from the system with small temperature differences. So if we have a heat pipe is a system that has a low air or non-condensing gas content. So the vapor, it gets filled with vapor, and it transmits then great amounts of heat from one side to another. So we have here this kind of a system. So we assume that we have a boiling temperature of 308 kelvins, and we have water in here, and it will cause some kind of pressure, not that much, but as an example, simple example. And we have the cold side temperature will be 10 degrees lower. And so when we get this water to be boiling at 308, we can cool on this side to 10 degrees below the boiling temperature. And we will have a greatly reduced pressure on this side. And as it is the pressures that determine the efficiency of these heat engines that each of these turbine blade rows represents, if we assume that we only would get couple of 2% of the internal energy of the heat by each of the turbine blade rows, and we would have lots of them. All of these blade rows would have at their different sites quite significant pressure difference. And what is important here is that the heat engine, as it takes internal energy of the passing fluid interacts with the border layer of this plate, so and gives the motive power to this each of the plates, and that they will rotate this generator here that removes energy taken from the internal energy of the molecules. It removes that from the system. So each of the plate rods will take some energy, and when all of the plate rods have taken so much energy that equals to the heat of vaporization, that is the major part of the heat that is added here to get the water into boiling. When the heat of vaporization has been removed, then the molecules will have intermolecular forces that are able to draw the molecules together, and they will collapse into liquid. And that liquid will be at the boiling temperature, and it will be causing the characteristic pressure of that liquid at the boiling temperature. And the heat engine will not be able to lower the pressure so that to the level that can be caused by cooling the liquid to a lower temperature than is the boiling temperature. So it's very energetically cheap to lower the temperature of the already condensed fluid. So if we have this kind of a system where we heat here the water's temperature by 10 degrees, so to the boiling temperature level, so we will need to be adding 42 kilojoules for 1 kilogram of water to get it 10 degrees warmer. But to vaporize this, the 1 kilogram of water, you would need then 2,257 kilojoules. So the heat of vaporization is an enormous energy taker, so to say. And that's why they are used in cooling your computers, for example, because they take lots of heat and transmit it through the heat pipe. So here, lots of heat is needed for vaporization, a little bit is needed for heating, and that heat of vaporization or heat of condensation will be removed by this, will be taken from the system with the turbine, and then it will need to be cooled by removing some heat, waste heat. It's to take 42 kilojoules for 1 kilogram of water will reduce its temperature by 10 degrees. And as we saw that earlier, so there's an enormous, when you just lower it by 10 degrees, you will have an enormous pressure drop. But it's in this kind of heat engine systems where the water is boiling at the very low temperatures, the pressures are also much lower. But choosing a right kind of fluid substance that for available temperatures, you will have significant pressures, and you will have the significant pressure drops when you lower the temperature by, let's say that 10 degrees. The 10 degrees is not kind of a necessary to use that kind of a small temperature. But if you want to heat this side with too much hotter, you can do it. This superheated steam will first lose this superheating to the turbine plate rows, and then after that will be the heat of vaporization will be taken. So you can basically heat it even after it has been vaporized. So and as we have here, let's see. I have nice pictures here, like this. Okay. No, not that one. There we have some. As I mentioned, that there are different substances that can power this kind of Hukkanen engine. And if we, for example, use let's see these waters. As I mentioned, so water is this here, and lots of fluid substances that behave very similarly. And if we have, for example, diethyl ether, it will be boiling at a lower temperature. And if we have here at the temperature of 5 degrees Celsius, and if we had that cold side temperature, and we have the hot side temperature of 15 degrees, so we will have these pressures inside of a heat pipe. And when we calculate the maximum efficiency, we will have maximum efficiency of 40%. So it's a kind of even if the pressures are quite low, it will operate with significant efficiency. All turbine plate rods can have a great pressure difference at the different sites. But if we have like water, have it boiling at 35 degrees, the difference to 45 degrees Celsius is the pressure difference is there, but the pressures will be quite low. Based calculated from these pressures, the maximum efficiency would still be 33%, but obviously the pressures are low. So it might be better to choose for if you have available temperatures like 70 degrees and 80 degrees. So you have higher pressures there, but it kind of shows that there is this, even if there is only a 10 degrees difference, you will have that high efficiency, and it will be transmitting great amounts of energy through the system, and that can be then taken from the system. And here we have, for example, to show this waters. You have at the boiling temperature 101 kilopascal saturated steam here. When you lower it by 10 degrees, like here, you will have 70 kilopascals vapor pressure. Yes, and if you cool it by 20 degrees, you will have something like almost 50 kilopascals. So it's kind of a and different substances follow kind of a similar behavior. So why is this important? There's a, okay, so what picture we take? Here. There's a quite heretic system as the uh, idea of heat being kind of a different kind of energies has been very prevailing, so that you might not be able to get all of the heat but from the system. But here I show that this is a totally heretic system. There is some kind of a Kelvin Planck statement that say that this would not be possible, but I say that the statement is, my statement is that their statement is wrong. And so if you have a heat pump, we would need to be removing heat, but if we remove the heat to this side of the heat engine, release it here, we have had that system operating with 98% efficiency because we were taking almost all of the heat of vaporization then with the heat engine. So we only need to be cooling it by a little. So we might use this energy produced by the generator to remove heat from this cold exit side to outside of this system, or even here. So this is kind of heretic system. But if we have we this kind of a system that has let's say it's a bus size thing, and what it put into the water, and we have 10 degrees temperature difference between the air above, and for example, during the winters, there's when there's a freezing temperatures here, somewhere, but so you will have hotter water, and you will have cold here, or you might have the other way around, but somewhere in different layers of water, or the layer above the water, there will be quite often the temperature difference. So we might be able to build a system where this heat is added to this side. It will cause the vaporization, and the pressure difference will be between the cold side where the fluid ends, and this kind of a thermosiphon like structure. So when the fluid comes to this side, we then kind of trap the fluid here, and we lower its temperature. We can uh, uh, lead this heat to some kind of cold heat energy receiving substance outside of the system, or using this heretic system. If we have a heat pump, we can return that small amount of heat to this side. So we will have a great pressure difference, and it will be powering this. And if you have a bus size system placed into water, then it will be kind of anchored to the bottom, and it will be just floating there, and it will be extracting heat energy from the water or sea or river or lake. This lake have also the temperature differences many times. No, well, many times a year it changes, but there are temperature difference also there. And the bus costs like 200,000 euros bus size device. From China, you might be able to get a bus for 200,000 euros. So let's assume that this would not cost much more. It's just a round tube, and there's a turbine inside of them. Just way to cool this side. and the way to lead energy into this, so that you can have heat pipes that are kind of extracting heat outside, or you can have this kind of a heat pump here that kind of circulates heat into the system. But the size of these systems is much smaller than, for example, wind turbine size. And these will operate with a much higher capacity factor because there is the uh, temperature difference more often available than is the wind. Might have in a shadow of and the sunny side might cause that difference too. So just put this side to the shadow and it will have this lower temperature there. So when you compare 1 megawatts of wind turbine with a 1 megawatt of this Hukkanen engine, it's a much simpler, much smaller structure. And if it costs like 200,000, then you will need to have 20 million of these to replace the entire current production of energy with the fossil fuels. And if you have this, is it possible to make 20 million bus-size things per year? Well, they are making like 20 million buses each year. So apparently it would be possible. So um, this can be done. This is much cheaper energy than with any other kind of alternative or fossil fuels. It's cheaper than gas. Maybe some Saudi Arabia might be able to um, produce almost competitive uh, oil, but it should not be kind of possible to do it much cheaper than this, because and this is much better. And what you can make with this electricity, well, you can make hydrogen. And when you have hydrogen, you can power, for example, your automobile. So you can use this electricity to make other synthetic fuels, methane gas or other ammoniac. There are alternatives for this. Methanol might be one. So or hydrogen. I believe that the hydrogen will become the winner of the uh, this new fuel race as we are replacing the fossil fuels, because when the heat engines can be made much more efficient, you will not be needing a massive hydrogen tank. When the efficiency goes over 90%, you will have you will need a hydrogen tank that is maybe 1/3 of its current size. So the hydrogen tank will be reduced from 200 plus liters to, let's say, 60 liters. And that hydrogen tank can power you as the same distance you get from the 200 liters tank. But to have a 200 liters hydrogen tank in an automobile, it's kind of too much. It takes too much space. It's unpractical. And but it will be a size of a normal gasoline tank, so then it can be possible. And this energy will be cheap. It can be operated with different kind of to operate vehicles. It can be operated with different power plants. You can make power plants and vehicles, airplanes, ships to work with 90%, over 90% thermal efficiency. So you will need lots of less fuel for the same distance and to travel a certain distance, and you can have those alternative fuels. So they will be competitively priced with this current fossil fuels. There will be no need for these fossil fuels. So let's see here what we have. The consequences: oil, wind, and nuclear power. So this will be cheaper than the fossil fuels. And the result will be that it will be replacing all fossil fuels because it's cheaper. The markets will decide that this will be the end of fossil fuel companies. It will destroy the value of their oil and gas reserves. I'm sorry about that. And it will significantly disrupt the fossil fuel economies. There are lots of countries that have most of the international trades profits coming from the fossil fuels. I'm sorry about that, but this will be destroying those incomes, and it might be causing violence and chaos. Sorry about that too. So it will be. It will cause enormous change. It's almost 10% of the world's population, I believe, have their income coming from fossil fuel industry, fossil fuels. So it's kind of an enormous economic shock for those nations. So it will be cheaper than wind and nuclear. There's no need to build nuclear power. There's no need to be building wind power, and better option for the environment. There will be no massive disasters with nuclear, and like wind turbines' ability to kill all kinds of flying things, and that's kind of not good. Birds like when the wind turbines disappear. These things that take energy from the heat of the water, heat of the seas. These can be placed quite nicely to the coastal areas. They will not cause any kind of disasters there. Automobiles will have enormous changes. The current lithium battery powered cars will become less eco-friendly when we compare this to burning even fossil fuels, because if the efficiency of the engine goes to over 90%, then the lithium battery powered cars will never achieve an equal consumption of the Earth's resources, because it's these lithium battery powered cars. They have their own environmental impact, but the best thing is that when this energy that my Hukkanen engine will be producing will be used for creating synthetic fuels or hydrogen that can be then powering the automobiles, then this is the kind of an alternative to this current electrification trend. Maybe there will be some kind of a new enormously great battery. There probably will be such, but these lithium battery powered cars will not survive this. So this disrupts the electric car business. Sorry about that. And I believe that initially it will be the resurrection of the gasoline-powered cars, and the rise of the synthetic fuels will, and all hail the hydrogen vehicles. Those might be kind of good for powering the uh, ships and airplanes too. So as I see it, this is kind of a important innovation slash discovery. It will be causing problems. You are welcome to try to make this thing not work. You will not succeed. And well, I assume that I will be getting even a Nobel Prize in Physics for this. So I thank the Nobel Committee in advance. Okay, so that was kind of it. I don't know what will happen. What will I do with this in 10 days? I might be letting this thing to go to internationally to public domain. I might be taking just the patent for Finland, and or I may be, if somebody is interested in this, we might be able to. It might be better to make this change slower because they are kind of a big impacts that may need some time uh, to be kind of a less harm, to cause less harm. So I'm open to suggestions, but for some strange reason, no one has been willing to kind of calculate and verify everything. I have calculated everything many, many ways, and no one seems to find any kind of problem, but not many people are much trying either. Feel free to try. You will fail in disproving this thing because it works. So I think that's all. Cheerio.